Let us continue with the seminar on object detection. We have ended up with this code, with a copy of this code basically. So now we're going to work with the same lines, but we're going to consider a different image as an input. We'll have this image, and we're going to try to detect certain objects with different colors, and we're going to use all the methods that we were talking about during the lecture. We'll consider some morphology on top of the color-based filter, and then connected components analysis. So let us first load this image and display it. I will substitute the opening of the camera with the reading of the frame. Excuse me, read. And here I have to substitute these lines with the copying of the original image into the frame. In order to do that, I will import a library that will provide us the necessary function. Now I can change the frame as much as I like to change it, and the original image will stay intact. So after that, I will probably apply some resizing because this image is rather big, and processing it could take much time. Also, it will be more convenient to show it on the screen. And one more thing that I have to omit here is, or to comment out here, is the closing of the camera, because we don't have any cameras right now. And as you can notice, this success flag is not used. That's because we are pretty much sure that once the frame is read, after that it will stay in the memory. So I will perform the resizing as follows. Width, height, channels number that we don't need, and it will be set to be equal to the shapes of the image. And here I can apply OpenCV's resize function like this. Hope that will not confuse anyone. Width divided by 2, like this, for it to be an integer, and height divided by 2 as well. So now we have a frame of a reasonable size, and let's try applying the same color-based filter as in the previous example. Okay, we have a typo here. Assertion failed. Okay, so let's try to find out what's going on. First, let's make sure that the image is being read properly. Yep. That's functioning. Oh. Wait, what? Okay, so the image is working properly, but something is missing here. And another thing is that here I have confused height and width of the image. I will comment this printing, or yeah, I will comment it. Okay, so let us print the shapes of this frame. First I will close this script and run it from scratch. Oh, excuse me. That should be a shape. Okay, so since we see these strange sizes of this frame, let us print the following thing. Let us print the size that we are trying to bring our image to. So let's find out what's going on. Here we see first the normal image sizes, and then they suddenly become equal to 7 and 4. And what can go wrong with that? How come? How could it happen? The problem here is that I have confused the name V, W, and H with the ones that were defined over here, with the width and the height of the connected component. That's a pretty tricky problem, pretty tricky bug to have. So let's avoid that, and let's call this image width and image height. And that will be fine. Also, we can simplify this code, and I think we can do it without deep copy, really. Let's skip that altogether. And now let's run and check. Oops. I'm printing the wrong stuff. I'm printing the height and the width of the connected component. So if I print it like this, it will be in, I don't know, 1000 and something. Yes. So that's just half of each of the spatial dimensions of the frame, and we're happy with that. So to do a quick recap, what's going on here? We're loading an image, we are resizing it, we're converting it to the HSV color space, and then we're applying color-based filter with the same default values as in the previous seminar when we were tuning the color-based filter to a certain object on the wall. Now we will have to retune the color-based filter to detect something, and first I think I will comment out the whole thing that is going on with the connected components filtration. Okay, so this is the mask, and we can set these thresholds to be 0 and the upper ones to be 255. Well, here you can clearly see that some objects are appearing from the darkness, and we will use the same logic as previously to detect them. So let's try to focus on just one object. Let it be, let's say, this ring. First I have to make the whole mask white, and you can pause the video and try to tune the filter so that only this object is visible. Well, it seems to be pretty easy to do. Although OpenCV is a bit laggy in macOS. but still. Here we can clearly see this shape appearing, and the majority of the rest of the mask is clearly black. There are some tiny bits of noise here and there, but still the solid and the only one big connected component in the mask is the one that corresponds to the object that we are trying to detect. So what can we do next is we can apply morphology, but that should be pretty clear at this moment, so let's skip that, and I will roll back the lower threshold. So can we filter the pixels by color so that we can detect all the objects and not detect the background? Can we do that? Let's try. So I will try to increase the values of the thresholds, of the lower thresholds, so that the objects are staying white and the background is black. Is it possible or not really? Well, here the orange cube is disappearing. And here the ball is disappearing. Well, here the black balls are disappearing. Here the circle is disappearing, and again, objects are disappearing, and I cannot really tune the filter doing that. So I have to make up some trick. Maybe I can solve an inverse problem. Maybe I can tune the color-based filter to react only to the background and then just invert the matrix. So let's do that. I can do that by substituting mask from 255. That's that easy. Or we can do it in a separate line. So as you wish. Okay, so now if we are tuning some, the default values are again from the previous example. So let's set the lower thresholds to 0 and upper thresholds to 255. So what are we going to see now? What do you think will be the result of running this code? Try to answer this question for yourself. And this one, the filtered, I will even remove that in order for it not to confuse us. So, no, that's not the correct one. Okay, so we'll show the frame and the mask, and the filtered one, we don't need it right now. Okay, so this mask is black, and that's because it's a negation of the mask that we get with these 6 thresholds. So now if we are going to increase some values of the thresholds starting from the lower hue, we will see some white objects appearing. What will it mean, basically? It will mean that we will tune the color-based filter to detect only the background, and then the mask will be inverted. So let's try. Okay, what do we see? Here we see that the objects are not here, and we are detecting basically the background. But since it's done in inverse, we have to roll it back like this. So let's increase the lower threshold again. We will basically increase the lower thresholds until some parts of the background will start to appear, like this in the left bottom corner. So we're getting some objects more and more until the background starts to appear. And the same goes with the higher thresholds. No. And the last one. That's pretty much it. So we can't really do anything much better than this with the color-based filter. And what we're going to do next is we're going to embed these values as the default values of the color-based filter, and then we will do some processing based on morphology, and then we will do the connected components analysis. So first, let's examine the mask. What's going on here? We have pretty solid masks for almost all the objects, including the ones that have some texture and bits of different color here and there, and the ones that are composed of two different colors, like these balls. The only object that is really difficult to call the one that has a solid mask is the pen. That's because of the light being refracted here, and we'll have to perform some operations to be able to detect it properly. The rest of the objects are pretty solid, and that will be much easier for us, but here we'll have to do some tricks. So first I will copy these values into the code. And let's double check. Yes, that's working. Okay, so let's start with the morphology. What can we do with it? First, we can get rid of the small objects that are appearing here, some bits of noise that are appearing here, and maybe even these ones. So let's try. First, I will create a kernel, and it will consist of ones. The shape of the kernel will be 3 by 3, and it will be basically filled with ones. It will have a type of enp uint8, and let me create a separate mask for that. It will be called morph. First, I have to pass the mask here, the input of the morphological operations. Then I have to pass, I believe, the type, so it will be something along the lines of cv2 morph open. And last but not least is the kernel. If I confuse the order of the parameters, it will just cease to work, so let's try. And yeah, one more thing that I have to do is I have to show the output. It's clearly better. Probably we can even increase the size of the kernel in order to get rid of these objects. Maybe that will work out, so let's try. I'm going to increase the size of the kernel. Let it be 5 by 5. Yes. So we have almost got rid of this tiny object, but the pen over here starts to disappear, and that's not fine. That's not good. So we can't really do much more with the morphological operations. We have to consider some connected components analysis. I will get back to the smaller kernel, and now I will uncomment this sequence of operations. So what's going on here? Just a quick recap. We are calling this function that will give us all these things as an output. The number of the connected components, the mask with the label of the connected component that is assigned to each pixel of the input, and the array with the statistics. From this array, we can extract the area of the connected component, top left corner, coordinates, width, and height. And it's enough for us to perform some filtering. So first of all, let us filter them by area. Okay, so if the area of connected component is greater or equal to 350, we will show it. Yeah. And I will delete some unnecessary lines here and there. It's better to keep the code clean. Okay, so yep, that's pretty much okay. One thing that confuses me is this. Seems like we have two connected components here. Do we really? Okay, so let us let us show only the connected component that has the area of 421. Ah, I get it, I get the problem. So here we are filtering the objects and it's all good, but the connected components analysis works on top of the original mask, not the mask that we are getting after the morphology. The connected component that is being drawn here is the one that corresponds to this area of connected pixels. So let's make sure that it's indeed like that. Let us show only the one connected component that has the area of 421 pixels. Hold on. Yes. Here it is. And in terms of the mask, let me... I will show even the mask for clarity. Filtered. Ah, it was already here, okay. I have to do it like this. So, yes. Here it is, this small connected component, and it has confused us slightly. Okay, now we can substitute it Again, we can change it to 350 or whatever, maybe 500. So now we're going to have only the proper objects, and can get rid of the unnecessary original mask and the output of the morphological operations. So now we have only the mask of the filtered connected components and the original frame. All these objects are detected properly, and we're pretty happy with that. So now let us try to detect certain objects, avoiding the detection of others. The first and the simplest thing to do is to use the area. That is pretty much straightforward. We will not do that. But what if we want to detect, let's say, only the pen? How can we do that? We have to consider some property of the pen that makes it unique among the other objects. And let us change this code. Let's try to print some different statistic, not the area, but something else. And it could be density. Density in the sense of area being divided by the product of the width and the height of the connected component. And probably we'll have to print only first 4 or so digits, because otherwise it will be just a very long float number, so we don't need that. And let's check. Here. So the theoretical value of the density that we are supposed to have while looking at a circle is pi over 4. And here we have something really close. Here we have something really close here as well. So yes, and here as well. 3/4, roughly. So if we're trying to detect a circle, that could be a good landmark or just a good feature for us. We can filter all the other objects out using the density. And the problem that arises here is that at a certain positions, let's say if this cube is rotated counterclockwise slightly, it could have such a density as the circles. But the great news here is that it will not happen that often. So if we are trying to tune some filter, some classical simple filter that's interpretable and that we have to do in a short amount of time, we can do it with the density and it will be fine. And regarding the pen, it has a density of 0.08. That's a very low value. So we can clearly remove all the other objects using this characteristic. Let's go through all the objects and try to outline how are we going to approach their detection. This ball could be detected using the unique blue color. This cube can be detected using unique green color. The same goes here, and the same goes here, but well, probably we'll have some problems with this black color that will appear here as well. So we can try either detecting only the green areas, if that will be fine for us, or we can avoid detecting any areas that have blue in its neighborhood. Okay, this object could be detected by color. That is pretty much distinct here. Well, here's the face of the cube and it's orange with the same shade, but this one is much smaller. This object could be detected clearly by its unique color. This object could be detected by color, which is pretty close to the surrounding, but it's not really the same one. And among all the objects, it could be clearly detected by the area, which is very small. And for this pen, we can use the density as a very good feature because it's described by a density that is lower than, say, 0.2. If the pen is not horizontal, of course. If it's horizontal, that will become much more tricky. And there are some other techniques. For instance, we can use the centroids, so we can calculate the elongation of the object. And for all the objects except for the pen, the ratio between the longest dimension and the shortest dimension will be pretty close to 1. And for the pen, it will be not like this. But we will not do that right now. For a quick recap, what have we done? Basically, we have applied an inverse color-based filter, so to say. We have detected only the background, avoiding all the objects, and then we have inverted the matrix. And after that, we have applied a morphological operation, and after applying morphology, we have filtered the objects using different criteria. In a great detail, we have considered density as a way to filter different objects. That's it for this seminar.